one of the big mysteries with antimatter is the bigger why. Where is the antimatter that should kind of be there if the whole idea is that anytime you generate matter, you generate the same amount of antimatter? And yet when we look out into the observable universe, it seems like there's not antimatter for the most part there.
Correct.
So what do we understand about this mystery? What are the possible explanations as to why?
So there's this thing called baryogenesis. And as you say, so reiterating a little bit what you just said, these are both Einstein things. Einstein says that when you take energy, you make matter and antimatter in equal quantities. And Einstein says after the Big Bang, there was a lot of energy in the universe, which should have made matter and antimatter.
Mm-hmm.
We only see matter. Where'd the antimatter go? And the answer is we don't know. However, there are some ideas, and there's a lot of thinking on it. And in fact, for me, is doing an experiment right now with neutrinos, trying to better understand what it was that made the matter and antimatter not be the same. Now, we do have a measurement of how much different it should be, and it's kind of neat. We can do this by counting the number of protons in the universe, just looking at galaxies and so forth. And then we can look at the cosmic microwave background, which is sort of the aftermath of the Big Bang, and we can count the number of photons from the cosmic microwave background. And with a little bit of math, what we can do is we can then say that somehow in the early universe, something made a very, very tiny asymmetry, so that for every billion with a B, antimatter particles that existed in the universe, there were 1,000,000,001 matter particles.
Mm-hmm.
The billions canceled, annihilated, destroyed each other, and that extra one that's left over is us.
Mm-hmm.
And so what physics mechanism made that ever so slight asymmetry is not understood. There are some thoughts. One thought is that, well, it's just how it was. When the universe was formed, there was an asymmetry. It was not made by matter and antimatter. Another possibility is there are various numbers of theories all under the word baryogenesis. And baryo coming from word baryon, which basically means protons, and genesis meaning the creation of. And we'd say that simply because the protons are the heaviest particles. And so baryogenesis is just the creation of matter. And there are just a number of theories in quantum mechanics that say that matter and antimatter can oscillate back and forth into one another, and there is a slight asymmetry in how that happens. And we know that this is true to a degree. We've measured it in the 1960s with a different form of matter. I mean, not protons, but a type of ephemeral matter that only exists in particle accelerators. And so we know that there is a slight difference between matter and antimatter, but it's not enough. It doesn't explain that. We're not sure. So at Fermilab, we have this idea which kind of turns things on its head, and it's not baryogenesis, it's leptogenesis. So leptons are the electrons. And because Fermilab is currently the world's most powerful neutrino accelerator, and neutrinos are leptons, there is this idea. Now, leptogenesis is incredibly complicated, but the idea is that it is possible. We know that neutrinos actually change their identity. There are 3 different types of neutrinos, like, cats and jaguars and tigers. And if you have a beam of just cats, if you go along a little while, you find there's cats and jaguars and then tigers, and then they'll be back to all cats again. And so this oscillation thing is called neutrino oscillation. We've known it's been true since 1998. And what we are studying is we're going to make a beam of neutrinos and another beam of antimatter neutrinos, and we're going to study the oscillation behavior of the two of them. And it is possible, it is unlikely, but it is possible that the two of them will oscillate at slightly different rates.
Mm-hmm.
And if the neutrinos oscillate at slightly different rates, then that, along with several other highly improbable things, can tie together and might explain why there is more matter in the universe. So if I was going to bet the farm, I'll bet that they oscillate at the same rate, but I don't know. And you don't know till you do the measurements. So that's what we're doing. There are some other experiments trying to measure it right now. So there's a big race between the Fermilab group and another group in Japan to see who gets there first and make this measurement. And we will find out. If it turns out, though, that there is a difference in this oscillation rate between matter and antimatter, it will be a huge clue in this very, very difficult puzzle. I wish I could tell you I knew what the answer is, but literally nobody knows. I mean, and that's the thing of being a research scientist like me, is if you're not confused, you're not doing your job.
So there is this desperate, or not desperate, exciting search for this tiny asymmetry.
Yes.
It's so crazy to think that everything we see around us is a result of this tiny asymmetry, that there was this gigantic annihilation of matter and antimatter in the
Yes.
early universe. And this is just some little accident.
Yeah.
Yeah,
Yeah. That's
it's a
crazy.
happy accident.
That is just, I mean, it's totally crazy.